Okay, so let us start today's session. Okay, in the last session, we have finished with the refrigerants. Okay, we have seen the properties of the refrigerant, how to designate the refrigerant. Okay, what you can understand from the designation, what physical properties the refrigerant should have, what chemical properties the refrigerant should have, how the refrigerants are classified, okay, like primary refrigerants, secondary refrigerants, okay. Further, what are the types of primary refrigerants, okay. So all these things we have seen in the last session, okay. Now for this session, okay, we'll be starting with the air refrigeration system. Okay, we'll be starting with the air refrigeration system. Okay, sometimes it is also called as aircraft cooling system. Okay, it is also called as aircraft cooling system. Okay, so in aircraft, okay, air refrigeration system is used in aircraft. Air refrigeration system is used for air refrigeration, okay, or air cooling. So let us start with that. Okay, so in order to start, okay, we will first study, okay, what is Bell Coleman, okay, or it is also known as reverse Briton, or it is also known as Joule cycle. Okay, so on one side you have a schematic diagram for the Bell Coleman cycle. Okay, I repeat, this Bell Coleman cycle, it is also known as reverse Briton, okay, or this is also known as Joule cycle, or this is also known as Joule cycle. Okay, see, in the thermodynamics we have seen Briton cycle. Okay, so the major difference between Briton cycle and reverse Briton cycle, okay, if you see, okay, the arrow which was going from 2 to 3, it is on the left hand side. Okay, that means from 2 to 3 we are cooling in Briton cycle, sorry, in reverse Briton cycle. Okay, but in Briton cycle what we are doing, from 2 to 3 we are heating. Okay, so if it is Briton, the point number 3 will lie on the right side of the point number 2. Okay, so point number 3 will be somewhere here. So if you want, okay, I'll just annotate it. Okay, see, if it's a Briton cycle, okay, your process will be like this. Try to understand. If it's a Briton cycle, your process will be like this. Okay, the point number 3 will lie here. Okay, point number 4 will lie here. Okay, and your process will be like this: 1, 2, okay, 3, okay, and then revert back to 4 and then 1. Okay, so this is, you can see this 1 if you want, this is 2, then this is 3 dash, and this is 4 dash. Okay, so 1, 2, 3 dash, 4 dash, it's a Briton cycle. Okay, what we have seen, okay, in the thermodynamics. Okay, is that okay? Are you able to recollect this? What is Briton cycle? 1, 2, 3 dash 4, it's a Briton cycle. Yeah, is that okay, all of you?
Yes, sir.
Okay.
Yes.
Now in this, in the HVAC, okay, what we are seeing, it's a reverse Briton cycle. Okay, so I will just clear now the annotation. Okay, I'll just clear the annotation. Okay, so the point number 3, which is lying on the right hand side, now it is lying on the left hand side. Okay, so point number, we will move from point number 2 to point number 3. Okay, so let us go with every process. Okay, now let us start with this process 1 to 2. Okay, so 1 to 2, it is a compressor. Okay, what is 1 to 2? 1 to 2, it is done in the compressor. Obviously that means it's a compression. Okay, 1 to 2, which is done in the compressor, obviously it will be a compression, because in compressor what happens is a compression. Okay, now let us see 2 to 3, 2 to 3. Okay, in 2 to 3, it is done in what? It is done in cooler. Okay, so by just name also you can understand. Okay, we need to cool it. Okay, now let's 3 to 4. Okay, it's a expander. Okay, so expander, you can see it is reverse of compressor. Expander, okay, you can see both the components I have placed exactly in a reverse manner. Okay, compressor, it is at the top, expander, okay, it is at the bottom we have. Okay, so what expander will do, it is work exactly opposite to that of compressor. Okay, so in expander, obviously we will expand it. Okay, so in expander, expansion will occur. Okay, now what happens in 4 to 1? What happens in 4 to 1? It's a refrigerator. Is a refrigerator. So here what happens is, okay, air gets heated. Okay, you can see this process 4 to 1 because the air will absorb the heat. Okay, air will absorb the heat. As a result, what will happen? It will be get heated. See, in the refrigerator, what we want cooling. So when you will get cooling, when we will abstract the heat, and when we'll abstract the heat, what happens? Okay, the air gets heated. Okay, so this is how the refrigerator works. See, in refrigerator you get cooling, but you will get cooling how? When the heat is being abstracted, and when we abstract the heat, okay, and what we'll do, we will it will be get heated. Okay, so now let us start with the PV diagram. So let us start with the PV diagram. 1 to 2, 1 to 2, it is done in a compressor. So you can see the process 1 to 2. Okay, it's a compression. It's a compression. Okay, but this compression is isentropic compression. Okay, this compression is what? Isentropic compression. That means the law which governs the compression, okay, it's PV raised to power gamma is equal to C. Try to understand the law which governs the process. Okay, that is a process 1 to 2. So the process 1 to 2, it's a isentropic. So isentropic means that, okay, it is governed by law PV raised to power gamma is equal to C. Okay, so 1 to 2, it's a isentropic compression which occurs in a compressor. Okay, now when we see, okay, or when you see this TS diagram, okay, you can see the TS diagram for this. So during 1 to 2, what happens? Okay, during 1 to 2, what happens is entropy remains constant. You can see S1 is equal to S2 because 1 to 2 is isentropic, right? Isentropic, it is nothing but what? It's adiabatic, right? So during 1 to 2, okay, that is during compression. See, this process, okay, the arrow is going upward. It indicates it's a compression. Okay. Now for isentropic, I need to mention the word whether it's isentropic. Otherwise, I need to mention the law that is PV raised to power gamma is equal to C. Okay, so here I've written isentropic compression. So 1 to 2, okay, it's isentropic compression. That is during 1 to 2, you can see entropy is constant. Okay, because we are plotting it on a TS diagram. So when we will plot it on a TS diagram, okay, that is isentropic process. Okay, it should be a vertical line, right? So now see, the question will be why I am moving upward. From point number 1, I can also move downward, okay, in a vertical direction. See, the process, it is of compression. The process is compression. So whenever the air gets compressed, what happens? Its temperature also increases. Okay, that is the reason why I am going upward. See, from point number 1, I can move downward or I can move upward. Now, why I'm moving upward is it's a compression. That is the reason why I am moving from point number 1 to point number 2, okay, in upward direction. Okay, because it's a compression, right? Now see, once I reach to point number 2, okay, you can see the 2 to 3, it's a cooling. Okay, 2 to 3, it's what? Cooling, and it is done in cooler. Okay, but this cooling, it is done at constant pressure. You can see on the PV diagram, it's a horizontal line. Okay, so if you have a horizontal line on a PV diagram, it's a constant pressure process. Okay, so during 2 to 3, okay, pressure is constant. Okay, so by keeping the pressure constant, we are cooling the air. Okay, we are cooling the air. Okay, so during 2 to 3, what happens is pressure remains constant. Okay, and air gets cooled. Air gets cooled. Okay, now see this 2 to 3, we have plotted on a PV. Let us plot on a TS. Okay, so what happens during 2 to 3, as you can see, okay, see during 2 to 3, okay, pressure is constant. Okay, so this is a constant pressure line. You can see this 2 to 3 line is a constant pressure line along which, okay, if you take the pressure at any point, it is constant. Pressure at any point on this line, it is constant. That is P2 is equal to P3. Okay, now question is, okay, why we are moving down? See, from point number 2, we can also move in a vertical direction along this line. See, if you want, okay, I will also show that to you. Okay, so from point number 2, you can also move it like this. See, you can also move in upward direction. Okay, but why we are moving in a downward direction is, okay, here the cooling occurs. You can see the arrow is going on the left hand side, so it indicates it's a cooling. So whenever it is cooling, what happens? Temperature decreases as well as the entropy decreases. That is the reason why I am going down, because during cooling what happens? Temperature as well as entropy decreases. That is the reason why I am going down. Okay, but if it is heating, I can go upward. So during heating what happens? Temperature increases, entropy increases, so that I can go upward. Okay, but what is expected during 2 to 3? Okay, by keeping the pressure constant, okay, by keeping the pressure constant, we need to cool it. Okay, so when I move from point number 2 to point number 3 along this line, pressure is constant. Okay, but okay, as it's a cooling, what happens? Temperature also drop downs. Okay, entropy also drop downs. Okay, now let us move. Okay, from next process 3 to 4, you can see the process 3 to 4. Okay, see, 2 to 3 we are conducted in a cooler. 3 to 4 it's a expander. So let us see this process 3 to 4. So 3 to 4 process, as you can see, it is exactly the reverse of 1 to 2. Okay, so 1 to 2 was a compression, 3 to 4 is expansion. Okay, but both are isentropic, right? Both are isentropic, which are governed by law PV raised to power gamma is equal to C. Okay, so this 3 to 4 is a expansion. Okay, and that is isentropic expansion. Okay, now see, now I am at point number 3. Okay, now I need to expand isentropically. So from point number 3 again, okay, I can have two possibilities. I can go either okay, or yeah, I can go either upward or I can go downward, right? Now see, from point number 3, why I'm see, from point number 3 I need to expand. Okay, I need to expand. So during expansion what happens? See, 3 to 4 it's isentropic. That means entropy at point number 3 and entropy at point number 4 is the same. Okay, just a minute. Okay, so see, I am at point number 3. Okay, process 3 to 4 it's isentropic expansion. That means from point number 3 to 4 entropy has to remain constant. That means, okay, point number 4 will lie on a vertical line. Okay, now if it is lying on a vertical line, again there are two possibilities, right? Which are those possibilities? You can move either in upward direction or you can move in a downward direction, right? You can move either in a upward direction or you can move in a downward direction. See, from point number 3 you can move either upward or you can move downward. Now see, when you go upward, what happens? The temperature will increase. Okay, when you go upward, what happens? Temperature will increase. But see, the 3 to 4 is an expansion. Okay, so what we want the temperature to decrease. Okay, so that is the reason why we are moving from 3 to 4. You can see 1 to 2, 3 to 4. They are a straight vertical line on a TS diagram because they are the isentropic processes, right? Now from point number 3, there are two possibilities. Okay, so as to get point number 4, you can move either in upward direction or you can move in a downward direction. See, if you move in upward direction, okay, what will happen? Temperature will increase. Okay, but we have expansion. That means what? Temperature has to be decreased. Okay, so that means we should get point number 4. Okay, here. Okay, that is just below the point number 3. Okay, is that okay? Yes, all of you.
Yes, sir.
Okay, now let us go to the process 4 to 1. Okay, as I told you, 4 to 1 it's a reverse of 2 to 3. 4 to 1 it's a reverse of what? 2 to 3. So during 2 to 3 we will cool. Okay, during 4 to 1 it's get heated. Okay, during 2 to 3, okay, air gets cooled. Okay, during 4 to 1 air gets heated. Okay, so 4 to 1, okay, during which the air gets heated, it is done at what? It is get done at constant pressure. Okay, so when we move from point number 4, okay, again you will get some line like this. So from point number 4, okay, these are the lines, right? So from point number 4, okay, we have this line. Let us see, this is a constant pressure line. See, from point number 4, this is a constant pressure line. Just see this. This is a constant pressure line. Okay, so from point number 4, there are two possibilities. Okay, on this line, either you can move, okay, on the left hand side, okay, or you can move on right hand side. That means from point number 4, you can move, okay, below, or you can move above the line, okay, on the line. Okay, you can move below on the line, or you can move above on the line. Okay, so these are the possibilities, two possibilities. Now from 4 to 1, what is happening? Okay, it's air gets heated. Okay, so whenever here air gets heated, okay, what happens? Temperature as well as entropy will increase. So from point number 4 to 1, when air gets heated, obviously temperature as well as entropy will increase, and this is possible only when we move in a vertically upward direction. That means when we move on the constant pressure line, okay, in vertical direction, you can see, sorry, in above. Okay, we can move on constant pressure line above. Okay, so we will move from point number 4 to 1, okay, like this. We will not move down, because when we move down, what will happen? Temperature as well as entropy will decrease, and this happens in cooling. Okay, when temperature and entropy decreases in cooling, but 4 to 1, it's heating. So obviously temperature as well as entropy has to be increased. Okay, that is the reason why I am moving on a constant pressure line, okay, above. Okay, is that okay? Yes. Is that okay with this one? Have you understood the diagram? Yes.
Yes, sir.
Okay, so this is what the Bell-Coleman cycle is. Okay, so this Bell-Coleman cycle, this is also known as, okay, Bell-Coleman cycle. This is also known as what? This is also known as reverse Briton cycle, or this is also known as Joule cycle. Okay, Bell-Coleman cycle or reverse Briton cycle, or this is also known as Joule's cycle. Yeah, is that okay? Have you understood the PV diagram? Have you first understand the schematic diagram, then PV diagram, followed by the TS diagram? Yes.
Yes, sir.
Okay, so this is all about, okay, Bell-Coleman or reverse Briton cycle. Okay, now let us move to the next part. Okay, now we need to analyze this cycle. Okay, we need to analyze this cycle. Okay, so what I've done basically is, okay, I have just made this thing, okay, in the PPT. Okay, and I just posted the picture of that PPT here. Okay, because some part it's not been, okay, compatible with the Google Slides. Okay, so that is the reason why, okay, this is appearing as an image. Okay, let us start with the analysis of the cycle. See, analysis of the cycle. Obviously, what do you mean by analysis? Okay, it's a refrigeration cycle. You can see we have started with what? Okay, air refrigeration system. Okay, air refrigeration. So our final purpose will be to calculate COP, right? Because it's a refrigeration system. Okay, you can't calculate efficiency. Okay, we need to calculate what? We need to calculate COP. Okay, so COP requires what? COP requires, okay, what desired effect you have divided by what work input you supply. Okay, so let us start working out on that. Okay, so let us come back to this diagram. Okay, now see, during this process 2 to 3, during this process 2 to 3, air gets cooled. Okay, during the process 2 to 3, air gets cooled. That means what? Air will reject the heat. Okay, see, when the air gets cooled, the air gets cooled only and only when it rejects the heat. So when any objects reject the heat, it gets cooled. Okay, so if you need to calculate what amount of heat that is rejected in the cooler, okay, how to calculate amount of heat rejected in the cooler? So heat rejected, okay, per kg of air is given by, okay, during which process the air gets cooled? That is during 2 to 3. You can see Air gets cooled during which process? During 2 to 3. So heat rejected will be the heat rejected during process 2 to 3. And see, the process 2 to 3, if you can see the process 2 to 3, okay, this 2 to 3, it is done at a constant pressure. As you can see, the process 2 to 3, it is done at what? Constant pressure. Okay. So see, both the cooling and heating occurs at a constant pressure, right? So see, as it is done at a constant pressure, okay, what is the formula? Cp into, okay, T2 minus T3. Remember, see how to calculate heat rejected in the cooler. See, this 2 to 3, that is cooling, it occurs in a cooler, okay, where pressure is constant. Okay, so if pressure is constant, how to calculate heat? Okay, heat transfer, okay, basically Cp into, okay, change in temperature. Cp into change in temperature if pressure is constant. Okay, if volume is constant, then Cv into change in temperature. See, if pressure is constant, it is Cp into change in temperature. Okay, if volume is constant, it is Cv into change in temperature. Okay, if temperature is constant, okay, how you will calculate heat transfer? So if temperature is constant, heat transfer is directly equal to work transfer, right? If entropy is constant, there is no heat transfer. Okay, I will not go into the detail of all those processes. Okay, let us see about this 2 to 3. 2 to 3, it's a constant pressure process. So if we need to calculate the, see, 2 to 3, it's a constant pressure process, that is constant pressure cooling. So during 2 to 3, what happens is heat gets rejected. So if we need to calculate what amount of heat is rejected, okay, how you'll do that? So 2 to 3, it is done at a constant pressure. So it is Cp into change in temperature. Now see, when you see the TS diagram, you can see that T2 is greater than T3. See, what is T2? It's the initial temperature. Okay, and what is T3? It's the temperature after cooling. Okay, so what happens? The T2 will reduce to T3. Okay, so T2 is the temperature. You can see the T2, it's the inlet of the cooler, and T3 is the outlet of the cooler. Okay, so obviously it's a cooler, so it will cool it. Okay, so we will get temperature T3 less than T2, as you can see in the diagram. Okay, so that means T2 is greater than T3, right? So what is change in temperature? Okay, it is T2 minus T3. Now see, many of you have faced the doubt. Why you're not taken final minus initial? Okay, you want it to be T3 minus T2, that is final minus initial, because, but see, all of you, I have clearly mentioned here heat rejected. So heat rejected, I already mentioned. Okay, I mentioned it as a heat rejected. Okay, so it is Cp. So what is heat rejected? See, when you take it T3 minus T2, what happens? You will get a minus sign, right? When you take it as T3 minus T2, okay, so we will get a minus value. Okay, so but here I have clearly mentioned it's a heat rejected, so it is understood that this term is minus. Okay, whenever heat is rejected, it is always minus. Whenever heat is absorbed, it is always plus, right? So here I have mentioned, you can see here T2 minus T3. Okay, because you can see that T2 is greater than T3. Okay, T2 is greater than T3. Okay, so what we'll get? We will get T2 minus T3, and this entire term we will get it as a positive value. Okay, this entire term we will get it as positive value. Okay, and that means it's a heat rejected. Heat rejected is how much heat is rejected? Okay, let us say 50 kilojoule. 50 kilojoule is rejected. You can't say that, okay, minus 50 kilojoule is rejected, right? You can't say like this. You can't say like minus 50 kilojoule is rejected. You can't say like this, right? Okay, so when you see, when you mention the sign as a minus, it is understood that it's a rejected. Okay, but if you are not putting the minus sign there, okay, and if it is rejected, okay, then you need to mention that heat is rejected. See here, same what I done. I mentioned heat rejected per kg. Okay, and this sign I am taking as a, okay, initial minus final, because this initial temperature, it is more as compared to the final temperature, because during cooling what happens? T2 will decrease to T3. Okay, so I'm taking this as a positive value. Okay, now let us come back to this diagram again. Okay, now what happens? Okay, in the refrigerator, okay, air gets heated. Okay, air gets heated. Okay, so what happens? See, don't get confused. In the refrigerator, we are getting cooling effects. Okay, we are getting a cooling effect. Why we are getting cooling effect? Because refrigerant get heated. Okay, we are getting the cooling effect in the refrigerator because refrigerant as which we have seen in the last lecture, R12, R22, okay, R134A, all those are refrigerants. So in the refrigerator, refrigerants get heated. Okay, because the refrigerants carry or they abstract the heat from the food atoms. Okay, so food atoms gets cooled, but refrigerants get heated. Okay, similarly here in Bell-Coleman cycle, what is happening is air is working as a fluid. Okay, air is a working fluid, right? So in Bell-Coleman cycle, air is a working fluid. Okay, so that air gets heated. Okay, so here what happens, the air gets heated from 4 to 1. You can see this process, 4 to 1. So during 4 to 1 air gets heated. Okay, and see, during 2 to 3 air gets cooled, during 4 to 1 air gets heated, right? Now let us see about that. Okay, now see, whenever the heat is whenever the air gets heated, obviously, okay, the air will absorb the heat. Okay, so when air will absorb the heat, then only it will get heated. Okay, so that is nothing but heat received by the air. Okay, here heat rejected by the air. Okay, here heat received by the air. You can see heat rejected by the air in cooler and heat received by the air in refrigerator. And heat received is nothing but what? Heat abstracted, right? That you can call. Right, so now let us focus here on this one. Okay, so how to calculate heat absorb? Okay, again the process is carried out at a constant pressure. Okay, you can see this 4 to 1, it is done at a constant pressure, so it is Cp into what? Change in temperature. Now you can see here, okay, see 4 to 1 is a heating. 4 to 1, this process is heating. So what happens during 4 to 1 is, during 4 to 1, okay, the temperature will increase from T4 to T1. Okay, so as you can see, T4 got increased to T1. Okay, so what is the final temperature is T1, okay, which is greater, okay, as compared to the initial temperature, that is T4, obviously, because 4 to 1 is a heating. Okay, so here what I taken, okay, out of T4 and T1, obviously the T1 is highest temperature, so I will take it like T1 minus T4. You can see T1 minus T4. Always see here, T2 is greater than T3, T1 is greater than T4. Both I am getting as a positive terms. Yeah, is that okay? So here, you see, here you can see, here I am taking final minus initial, okay, but here I have taken initial minus final. I have taken initial minus final because it's a cooling. Here I have taken final minus initial because it's a heating. Okay, but here I mentioned heat rejected and heat absorbed. Okay, so is there any problem with this one? Yeah, let me know. Is there any problem with this one? Yes.
No, sir.
Okay, so now see, what is work done? All of you, how to calculate work done? See, it's a cycle, right? When we talk about this 1, 2, 3, 4 and 1 back, it's a cycle, right? So when system executes a cycle, okay, what happens is, okay, we have seen the first law of thermodynamics, okay, which is applicable for a closed system undergoing a cyclic process. Try to understand, just try to recall those concepts. Okay, first law of thermodynamics. Okay, we have seen it for closed, we have seen it for open. Okay, now by looking at the diagram, okay, it's not an open system. Okay, it's not an open system because same fluid is circulated again and again, air is circulated again and again, so it's not an open system. So obviously it's a closed system. Okay, so in closed system, okay, we have seen two parts. Okay, one is a cycle and second is non-cycle. Okay, so as you can see, this 1, 2, 3, 4 back to 1, it's a cycle. So what first law of thermodynamics for a closed system undergoing a cyclic process says, okay, is summation or cyclic integral of heat transfer is equal to cyclic integral of work transfer. Okay, that means okay, the heat gets converted into work, or total work gets converted into heat. Okay, net heat transfer is equal to net work transfer. Okay, so that is the reason why, okay, what I done, this W, okay, W is equal to what? Q. W is equal to, or net work is equal to net heat transfer. And what is net heat transfer? It is obviously heat rejected minus heat absorbed. Heat rejected minus heat absorbed. Listen, now here you might find, sir, we always used to take heat absorbed minus heat rejected. Okay, heat absorbed minus heat rejected, that we used to take. Okay, but absorb minus heat rejected, it is applicable for the engines where the power is gets produced. Okay, absorb minus rejected, it is applicable to the engines where power gets produced, because what happens in engines, okay, heat absorbed is greater than heat rejected. Okay, a simple example, for the engine you might supply 50 kilojoule. Out of 50 kilojoule, engine may convert 30 kilojoule into work, okay, and 20 kilojoule it will reject. Okay, so out of 50, 20 is rejected. Okay, out of 50, 20 is rejected. So what is power? 50 minus 20, that is 30 is a power. Okay, so as you can see, heat received by the engine, that is 50, it is greater as compared to the heat rejected, which was 20. See, engine is receiving 50, engine is rejecting 20. Okay, so all of you obviously, okay, 50 is greater than 20, because what the engine is doing, okay, out of some heat receives, some heat it converts into work, and some heat it rejects. Okay, so you can take absorb minus rejected for the engines, because absorb is nothing but heat received. Okay, so for engine, heat received is greater than heat rejected, because out of some heat received, engine rejects some heat. Okay, but this is not applicable for the refrigeration cycles. Okay, because in refrigeration cycle what happens, more heat is rejected as compared to the heat absorbs. Okay, see, more heat is rejected as compared to the heat absorbs. Okay, so that is the reason why I'm taking heat rejected minus heat absorbed, because how much heat the refrigeration cycle will reject, okay, it's the addition of how much heat it will abstract plus how much work you supply. See, if you just want to recap me, okay, I will just recap you if you're not able to get this point. Just give me a minute. Okay, see all of you. Okay, let us see. Okay, let us see about that. See, in the last session, okay, what we have seen, okay, I think that PPT, okay, we have it okay, in the form of Google, that in the form of that Paint app, I have it. Okay, so let us see that later on. Okay, see here all of you now. See, so let us try to understand. See, this is very important part which you're supposed to understand. Okay, so what happens in refrigerator, more amount of heat is rejected, okay, as compared to heat absorbed. Listen, what the refrigerator will do, refrigerator will abstract some amount of heat only and only when you supply the work. Okay, so heat abstracted plus what work you supplied, it is the heat rejected. Okay, so obviously heat rejected will be more as compared to heat absorbed, right? Is that okay, all of you? Yeah, let me know. Yes.
Yes, sir.
Okay, that is the reason why, because see, in refrigerator what happens, okay, refrigerator requires some work to be supplied so as to abstract the heat. So when you supply the work, the refrigerator will abstract. Okay, and how much it will reject? Okay, it's the addition of heat abstracted plus work supplied. Okay, so that means heat rejected, it is greater than heat absorbed. You can see this QR minus QR written. So let us put the value. QR is Cp into T2 minus T3 minus Q absorb. Okay, it is nothing but Cp into T1 minus T4, right? So this is work done we got. Now let us see about the coefficient of performance, what is called as the COP. Now how to calculate coefficient of performance? Coefficient of performance, okay, it is the basically it's a desired effect upon work input. What desired effect you have divided by work input, right? Work, desired effect by work. Okay, so is given by, now QA we already have it. Okay, you can see this QA, that is CP into T1 minus T4 divided by W. Just now we have calculated, so W I have written. Okay, so this is QA divided by W. Okay, all values are we already written. Okay, so is equal to, now CP is a common term as you can check. Okay, so CP will be get cancelled, so only remaining is T1 minus T4 divided by T2 minus T3 minus T1 minus T4. Now what I will do, okay, from the numerator I will take T4 common. From the numerator I will take T4 common. So when I take T4 common, it is T1 by T4 minus 1. You can check this T4 into T4, that is T1, then T4 into 1, it's T4. So you will get same T1 minus T4, right? In the denominator, okay, from the first term I will calculate, or I will take T3 common. So when I take T3 common, what is remaining? It's T2 by T3 minus 1. Similarly, from the second term I will take T4 common. So what is remaining is T1 by T4 minus 1. Okay, so I will call this as equation number 1. Okay, I'll call this as equation number 1. Is that okay with this one? Yes. Yes, all of you?
Yes, sir.
Okay, now let us see here, all of you. Okay, when we talk about the process, this 1 to 2, whether it's a 1 to 2 or whether it's a 3 to 4, both are isentropic. 1 to 2 and 3 to 4, they are isentropic. Okay, so whenever it's an isentropic process, see 1 to 2 is isentropic. It doesn't matter whether it's a compression or expansion. Okay, see isentropic, either it can be a compression or it can be expansion. Okay, so for isentropic process, okay, in the thermodynamics, okay, in the first chapter only we have derived the law. Okay, what was that law? Final temperature by initial temperature is given by final pressure by initial pressure raised to power gamma minus 1 by gamma is equal to initial volume by final volume raised to power gamma minus 1. Okay, I'm not writing that volume term. Okay, we'll focus only on the temperature and pressure terms. Okay, so let us see that. So final temperature by initial temperature is final pressure by initial pressure raised to power gamma minus 1 by gamma. So this is equation number 2, which I will call, see, I am writing this equation because 1 to 2 it's a isentropic process or it's a adiabatic process. Isentropic and adiabatic, it is same meaning, right? Now let us go to the process 3 to 4. Okay, so 3 to 4 again same, you can see 3 to 4, it's again a isentropic process. You can see 3 to 4, it's again a isentropic process, right? So I can write down, okay, for 3 to 4 again I can write down the same expression. You can see final temperature by initial temperature is equal to final pressure by initial pressure raised to power gamma minus 1 by gamma, raised to power gamma minus 1 by gamma. Okay, same on the similar line I am able to write down it. Listen, the equation you written, okay, this equation number 2 or equation number 3, you are not able to write down for the process. Okay, you can't write down for 2 to 3 and 4 to 1 because 2 to 3 it's not isentropic. Okay, 4 to 1 it's not isentropic, so you can't write down those equations. So you can write down such equations only for isentropic process, like for 1 to 2 and 3 to 4. Okay, so let us do that. Okay, so for 1 to 2 I've written, similarly for 3 to 4 I've written. Now what I will do, I'll just take a reciprocal of that. Okay, so T4 by T3 becomes T3 by T4. Similarly, P4 by P3 becomes P3 by P4. Okay, becomes P3 by P4. I just taken the reciprocal of this equation. Okay, what is about the power? It will remain same only. Okay, when you reciprocal it, okay, power doesn't change. It will remain same, right? So T4 by T3 you can write down as T3 by T4. P4 by P3 you can write down as P3 by P4. Okay, raised to power gamma minus 1 by gamma as it is. Okay, now come back to the PV diagram. Okay, you can see now P2 it is same as P3, okay, and P1 is same as P4. Okay, so let us put that. See, P3 is same as P2, P4 is same as P1. Okay, raised to power gamma minus 1 as it is. Okay, so let us write down these are the equation number 3. Let us write down these are the equation number 3, right? Now all of you, okay, you compare the equation number 2 and equation number 3. Okay, now compare these equations. Compare equation number 2 and 3. So when you compare equation number 2 and 3, you'll observe that their right hand side is equal. Okay, right hand side is same, that is P2 by P1 raised to power gamma minus 1 by gamma. Okay, here also right hand side is same. So that means you can equate the left hand side, and left hand side is what? For equation number 2 it is T2 by T1, for equation number 3 it is T3 by T4, right? So that means I equated that. See, this T2 by T1, it is same as T3 by T4, it is same as T3 by T4, right? So let us rearrange it. Okay, let us bring this T3 on the left hand side. Okay, so it will come in the denominator, and let us bring this T1 on the right hand side, so it will comes in the numerator. Okay, so this equation, okay, and this equation, it's one and same. Okay, it's a rearrangement of just temperatures. Okay, T3 I am bringing below the T2, T1 I am bringing above the T4. Okay, this is just a rearrangement. This is equation number 4 that you can call, right? So we got equation number 4 now. Okay, so purpose to get the equation number 4 is we need to put this value in equation number 1, right? We are supposed to put this value in the equation number 1, right? So what we'll do, okay, so let us put the value from equation number 4 into the equation number 1. Okay, and let us calculate the coefficient of performance. Okay, so this is a coefficient of performance, okay, is given by, okay, this T1 by T4, T1 by T4, okay, and T2 by T3, they are one and same, right? This T1 by T4 and T2 by T3, okay, they are one and same. Okay, so what will happen? They gets cancelled. Okay, see, T1 by T4 and T2 by T3, they are one and same, so they gets cancelled. So what is remaining? See this, instead of this T2 by instead of this T1 by T4, okay, see, this is T1 by T4, this is T1 by T4. What do? Instead of T2 by T3, na, you put this value T2 by T3, you put it as T1 by T4. So let us put this as T1 by T4. Okay, then what happens? From the denominator we will get T1 by T4 minus 1 common. Okay, and we also have the T1 by T4 minus 1 in the numerator, so it gets cancelled. So what is remaining? T4 upon T3 minus T4. It is remaining is T4 upon T3 minus T4. Okay, now what we will do here is, okay, I will just take, okay, I will just bring this T4 in the denominator. Okay, I'll just bring this T4 in the denominator. So when I bring this T4 in the denominator, what will happen? It becomes T3 by T4 minus 1. See, just T4 you bring it in the denominator. So it is T3 by T4 minus T4 by T4. So it is 1. Okay, so is given by this 1 as it is. Okay, so what is the value of T3 by T4? Okay, just we have that value, T3 by T4. You can see this value, T3 by T4. So this T3 by T4, it is nothing but what? It's a P3 by P4 raised to power gamma minus 1 by gamma. So same value I just put. So T3 by T4 is P3 by P4 raised to power gamma minus 1 by gamma, and it is same as what? P2 by P1 raised to power gamma minus 1 by gamma. So same I put, it is P2 by P1 raised to power gamma minus 1 by gamma. Okay, minus 1, right? So see, when you see this, okay, this P2 by P1, okay, we used to call it as, okay, it's a compression ratio, we used to call it as, sometime explosion ratio also we used to call it as. Okay, but in Briton cycle it is more specifically known as pressure ratio. Okay, so this is RP, I have written pressure ratio. P2 by P1 I will call it as RP raised to power gamma minus 1 by gamma minus 1. Okay, so this is the equation, okay, which we will get. This is the expression or expression we will get for calculating the COP of, okay, for calculating the COP of Bell-Coleman cycle. Okay, for calculating the COP of Bell-Coleman cycle. So how will you calculate the COP of Bell-Coleman cycle? Okay, it's the 1 divided by RP raised to power gamma minus 1 by gamma minus 1. See, RP is nothing but what? Okay, maximum temperature by minimum temperature. You can see here in the diagram. Okay, don't get confused between the notations which I'm using. Try to remember the basic formula. Okay, what is P? See, I'll just come back to the diagram. Okay, you can see here P3 by P4 or P2 by P1. Okay, P3 by P4. You can see P3 is a maximum pressure. Okay, P3 or P2, it's a maximum pressure. P1 and P4, they are the minimum pressures. Okay, so remember in the form like this. Okay, maximum pressure by minimum pressure raised to power gamma minus 1 by gamma minus 1. Okay, 1 upon maximum pressure by minimum pressure raised to power gamma minus 1 by gamma minus 1. Okay, so this is a best way how you can remember it. Okay, in terms of maximum and minimum, okay, everything, it's better that you should remember in this manner, right? So is that okay with this one? Yeah, all of you, have you understood this derivation? Yes, I'm asking
Yes,
for
sir. Understood, sir.
all of you. Yeah, all others, they also can respond.
Yes, sir.
Okay, okay. So this is how we are calculating the COP of Bell-Coleman. This is also known as reverse Briton. This is also known as a Joule cycle. See, so these are the three names. Okay, but the meaning is same. It's a Bell-Coleman cycle. Okay, so don't get confused between the names. It's a Bell-Coleman, or it's a reverse Briton, or this is also known as Joule cycle. So initially we have started with the schematic diagram, followed by the PV and TS diagram, and followed by the analysis. Okay, what do you mean by analysis of this refrigeration cycle? Is to calculate the COP, right? So now let us move to the next part. Okay, the next part, it talks about the necessity of air cooling in aircraft. Okay, why air cooling is required in case of an aircraft system. Okay, so that is what they are expecting. Okay, so see, why there is a necessity of air cooling in aircraft, or why there is a necessity of aircraft refrigeration system. Okay, that is one and same. Why aircraft refrigeration system is required. Okay, so that we need to see. Okay, so after seeing this necessity, okay, then only we can see the different types of air refrigeration system, okay, which are used in aircraft cooling. Okay, so first let us see why the air cooling in case of an aircraft is required. Why there is a need of air cooling in aircraft system. Okay, so after that we will see the types of systems which are available in aircraft for air cooling. Okay, so let us start first with that. Okay, so see, in case of an aircraft system, okay, when we talk about the aircraft system, okay, we need to maintain the cabin temperature, okay, such that it should be at a comfortable level, right? So in aircraft, what is required? Okay, we require that the cooling system should keep the cabin temperature, okay, which should be comfortable. Okay, so now even when the outside temperature is low, okay, still the cabin is required, the cooling is required in the cabin. Now see, let me give you a simple example, right? See, in aircraft, okay, what the cooling system required in aircraft, the cooling system required to keep the cabin temperature at a comfortable level. Okay, even when the outside temperature is very low, okay, still we want the cooling, because see, when the aircraft is traveling at a higher height, okay, that means at a higher altitude, okay, the temperature is low, okay, but still the cooling is required. Okay, what is the reason for that? Okay, still see, when the aircraft is traveling at a certain huge height, right, so obviously there the temperature is low, okay, but still the air cooling is required. And what is the reason for that? So let's try to understand the first reason. Okay, because see, whenever the aircraft, okay, is used to travel, right, what, there will be internal heat generation. Okay, due to what? Due to the occupants, okay, that means which are the passengers are there, okay, and the equipments are there, okay, and due to that there will be internal heat generation, and that internal heat generation, okay, it is at a larger extent. Okay, so large amount of heat is generated internally due to the occupants. Okay, that means you can have those passengers, all those, okay, and equipments which are there. Okay, so that causes large internal heat generation. Okay, now second is, the heat generation is also caused due to the skin friction, which is caused due to the fast moving aircraft. Okay, so whenever the aircraft is moving, okay, with a higher velocity, what happens? There will be some skin friction which is caused. Okay, and due to that, what happens? The heat gets generated. There will be heat generation, okay, due to the skin friction which is caused, okay, due to the fast movement of the aircraft. Okay, Now see what happens at higher altitude. Okay, outside pressure will be subatmospheric pressure. Subatmospheric, it is below the atmospheric. Okay, because at higher pressure, higher altitude, what happens at higher altitude? Okay, obviously the outside pressure is subatmospheric pressure. Okay, and when the air at this low pressure is compressed and supplied to the cabin at a pressure that is basically the close to atmospheric, the temperature increases significantly. Now see, simple example. At high altitude, what happens? The outside pressure is subatmospheric pressure. Okay, and when you have such air, or when you compress such air, okay, and when you supply that air, okay, to the cabin, what happens? Then temperature increases significantly, right? Because about outside we have what? Outside we have, okay, we have a very low pressure. Okay, and when you compress the air at this low pressure, what happens? Okay, the cabin pressure, it is close to atmospheric. Okay, and the temperature increases significantly. Okay, for example, just take the example. What happens when the outside air is at a pressure of 0.2 bar? Okay, and the temperature is 323 Kelvin. Okay, at approximately at, let's say, 10,000 altitude. Okay, and when you compress the air to 1 bar, see what happens? What is the initial pressure? It's a 0.2 bar. Okay, and what is the temperature? 223 Kelvin. Okay, at what height we have? At 10,000 meter. Okay, so these are the conditions. And when we compress it to 1 bar, what happens? Temperature increases to 353 Kelvin. Okay, you see a simple example we have given. So in that case, what happens? The temperature increases to 353 Kelvin. Okay, and what happens if the cabin is maintained at 0.8 bar? The temperature will be about 332 Kelvin. Okay, and see, if you supply this 353 to the cabin, okay, which is maintained at 0.8 bar, the temperature will be about 332 Kelvin. Okay, and this effect, it is called as ram effect. Simple. See what we have: outside air pressure we have as a 0.2 bar, and outside air temperature is 223 Kelvin at let's say 10,000 altitude, right? And when we will compress it, okay, when we will compress it to 1 bar, what happens? This 323 Kelvin, it increases to 353 Kelvin. Okay, so the when we increase the pressure, temperature got increased to 353 Kelvin, right? And when we supply this 353 to the cabin, okay, now what is the temperature of the pressure of the cabin? Pressure of the cabin is 0.8 bar, and when you supply this 353 to the cabin, what happens? The temperature becomes 332 Kelvin, and this effect, it is called as ram effect. Okay, and these effects add heat to the cabin. Due to what? The heat is added to the cabin. Okay, and this see, whatever amount of heat that is added to the cabin, okay, this is to be taken out by the cooling system. Okay, so that is the reason why the cooling system is required in case of an aircraft. Okay, so that is called as aircraft refrigeration system or aircraft cooling system. And fourth point, it is about the solar radiations. Okay, so the solar radiations which will be incident on the planes, okay, so they will also leads to heat generations. Okay, so now see, for the low speed aircraft, okay, which are basically flying at the low altitude, okay, so cooling system may not be required. Okay, because what happens when they are what you can say, flying, okay, on the low altitude, that is at a low height, okay, then all this thing, okay, will not work. Okay, so in that case, the air refrigeration system or aircraft cooling system may not be required. Okay, but when we have the aircraft which are flying at the high altitude, okay, so obviously the cooling system is required and it's essential. Okay, because what happens, okay, when you compress it initially, okay, what happens? Its temperature increases. Okay, but when you supply it into the cabin, okay, obviously again temperature decreases. Okay, that means the temperature got decreased. That means what? The heat gets added into the cabin, right? Into the cabin, because see, when you supply 353 into the cabin, it is expected that the 353 has to be maintained there. Okay, but what happens When you supply 353, okay, at 0.8 bar, okay, the temperature, okay, drop down to 332. Okay, so then what is about that difference in the heat? Okay, so due to that, what happens? Okay, the heat is added. Okay, and that heat added, it is called as ram effect, and that heat we need to take it out. Okay, that heat we need to take it out, and that is the reason why this air cooling is required. Yeah, is that okay, all of you? Yes, have you understood why there is necessity of air cooling in aircraft? Okay, that means why the aircraft refrigeration systems are required. Yeah, is that okay?
Yes, sir.
All of you, is that okay?
Yes, sir.
Okay.
Yes, sir.
So with this, okay, we will conclude the today's session. Okay, and in the next session, okay, we will see, okay, the types of, okay, air refrigeration systems, and those are simple air cooling system, simple air evaporative cooling system, bootstrap air evaporative, reduced ambient air, regenerative air. Okay, so here our most focus will be on the first, that is simple air cooling system, and bootstrap air cooling system. So first and third, okay, we'll try to focus more on them. Okay, so with this we will finish, and in the next lecture, okay, we'll continue, okay, these air refrigeration systems.